When we have 2-point charges, then the force F12 of the charge 1 on charge 2 is a function of the distance r. So we write this in functional form as the vector force F12 of r. If we wish to move the charge Q2 closer to the charge Q1, that's going to require some energy, assuming, of course, that these charges have like signs so that the force is indeed in this direction. Then to move the charges closer together, we're going to have to do some work. Now, if these are unlike charges, then we're actually going to have to restrain this one as it goes, and we'll be exerting a force in the direction opposite to the motion of the charge, and the work done, well, there will be a net work done on the charge by the force from Q1, and we'll sort all that out as we go. However, if we think of the situation here, we're trying to move a charge Q2 closer to Q1, then we have, if we move the charge slightly closer so that the distance delta r is small, then we have the force F12, which doesn't change a whole lot. F12 at r minus delta r, F12 at r aren't too much different. And in that case, we can say that the work that we have to do is equal to the force that we have to exert at this point to begin moving the charge times the distance. The force that we have to exert here is, of course, equal and opposite to F12 at r. So we assume that we exert a force F12 of r for distance delta r in order to move Q2 somewhat closer to Q1. Again, we're assuming delta r is small so that we don't have to worry about the difference between F12 of r and F12 of r minus delta r. So that the work that we do is equal to negative F12 of r times delta r. We're moving a distance delta r, and we're exerting a force equal and opposite to F12 of r. So the work that we do will be negative F12 of r delta r. We could approximate this a little bit more accurately if we really wanted to. If we were doing an approximation, we could average F12 at r with F12 at r plus delta r, although that would make this thing positive. So if we average the two forces and multiplied by delta r, we'd get a better approximation. But as long as delta r is small, our approximation will do okay. And in the end, it doesn't really matter, because what we're going to do is we're going to say that the total work done in moving from one point to another can be approximated by moving between those points in small increments, small delta r's, giving us small delta w's. And the total work that we have to do is equal to the sum of all those delta w's. And that sum approaches a limit. Now, this is calculus, so if you're in the non-calculus, if you're not in the university physics course, you can tune out for just a minute, but except to understand that this is just a way of summing up all these forces. Now, if you're in university physics, you'll see, of course, that this negative f of r dr is just an integral that's the limit of the sum of the delta w's, because if we do an f of r times delta r, we get a delta w. You understand the limiting process. Now the delta w is just the negative of f1 of r, so that our delta w will be negative f12 of r times delta r. Then the work that we do will be the sum of all these delta w's. The delta v that we get over a short interval will be delta w over q2, because q2 is the charge that we're moving, and delta v is the work done per unit charge. Okay, so the q2 experiences this force. It's q2 that's experiencing this force, so that the delta v that we get will be the work per unit charge, delta w over q2, which is just f12 of r delta r over q2. Of course, this being delta w, this being q2. Now the magnitude of this force is kq1 q2 over r squared. That is, F12 of r is kq1 q2 over r squared. And that's times delta r, and of course we're going to divide that by q2. And looks like I've messed up my signs here. That should be negative. And that, of course, should be negative because we're exerting a force opposite to F12. So I've lost my negative sign there somehow. It follows that the voltage at B minus the voltage at A, or your change in voltage, turns out to be an integral. Again, an integral much like your f of r dr, except that we're dividing f of r by q2 to get the voltage. And we should be integrating the negative of this quantity. So let's put a negative sign there. It's a bad looking negative sign, but we'll live with it. And then that integral, as university students will verify, comes out kq1 over b minus kq1 over a. And that's the difference in voltage. And we note that that difference depends only on the charge q1.